Oxford Ionics and Iceberg Quantum, Revolutionizing Fault-Tolerant Quantum Computing. Quantum computing's next breakthrough, when two innovators join forces to solve the error correction puzzle. Imagine a world where quantum computers can reliably solve complex problems without crashing midway. Sounds like science fiction, right? But two cutting-edge companies are turning this dream into reality, and their collaboration might just change everything we know about quantum technology. Oxford Ionics and Iceberg Quantum have just announced a groundbreaking partnership that could revolutionize fault-tolerant quantum computing. But here's where it gets fascinating: they're not just working together, they're strategically dismantling one of quantum computing's most stubborn challenges. The problem most people don't understand. Traditional quantum error correction methods have been notoriously inefficient, requiring an astronomical number of physical qubits to maintain just a single logical qubit. Think of it like needing an entire football team just to ensure one player can consistently catch a ball, wildly impractical. Enter qLDPC codes, the game-changing solution. Quantum Low-Density Parity-Check, qLDPC, codes are the secret weapon in this technological arms race. Unlike conventional error correction techniques, these codes offer a smarter, more streamlined approach to protecting quantum information. By utilizing sparse, non-local structures, they dramatically reduce the hardware overhead that has long plagued quantum computing development. Why this partnership matters? Oxford Ionics brings world-class trapped-ion quantum computing technology to the table, while Iceberg Quantum contributes revolutionary architectural expertise in qLDPC codes. Their collaboration, part of DARPA's Quantum Benchmarking Initiative, isn't just another research project, it's a strategic mission to make quantum computing commercially viable. The technical magic behind the scenes. Trapped ion hardware provides an ideal environment for implementing qLDPC codes. With exceptional long-range connectivity, impressive coherence times, and high-fidelity quantum gates, these systems can perform the complex, non-local interactions that make qLDPC codes so powerful. What sets this approach apart? While most quantum computing efforts struggle with error rates and scalability, Oxford Ionics has already demonstrated remarkably low error rates across critical metrics. Single-qubit gates, two-qubit interactions, and quantum state preparation are all performing at unprecedented levels of precision. The bigger picture: commercializing quantum computing. This isn't just about academic research, it's about creating quantum computers that can solve real-world problems. By reducing hardware requirements and improving error correction, Oxford Ionics and Iceberg Quantum are paving the way for quantum technologies that could transform industries from cryptography to drug discovery. Controversial question for readers: are we witnessing the moment quantum computing transitions from theoretical marvel to practical technology? Or is this just another overhyped promise in the world of tech innovation? We'd love to hear your thoughts. Drop a comment below and join the conversation about the future of quantum computing. Quantum breakthrough: Oxford Ionics and Iceberg Quantum tackle fault tolerance. The quantum computing revolution is closer than you think, but there's a critical roadblock everyone's ignoring. Oxford Ionics and Iceberg Quantum just revealed an ambitious partnership that could redefine how we achieve error-resistant quantum systems. While most companies chase short-term quantum milestones, these collaborators are tackling the elephant in the room, making quantum computers reliable enough for real-world use through advanced error correction. Here's the breakthrough: Oxford Ionics will develop next-gen quantum computer architecture specifically designed to implement Iceberg Quantum's cutting-edge qLDPC, Quantum Low-Density Parity-Check, codes. Think of these codes as a spell-check system for quantum calculations, except they fix errors in real time during complex computations. But here's where it gets controversial: some experts argue alternative error correction methods like surface codes might offer better short-term results. Could this partnership be prioritizing theoretical elegance over practical implementation? Want to understand why this matters? Let's break it down. Quantum bits, qubits, are notoriously error-prone due to environmental interference. Fault-tolerant systems use error-correcting codes to maintain accuracy, like having backup singers keeping a pop star's vocals pitch-perfect during a live show. qLDPC codes promise to do this more efficiently than current methods, potentially requiring fewer physical qubits per logical qubit. Now here's the kicker, the companies are offering exclusive access to their progress through Scientific Computing's Premium Content Hub. By registering, free at the link below, you'll get behind-the-scenes analysis of HPC-AI integration in quantum development. Case studies showing how life sciences labs are already benefiting. First looks at breakthrough papers about hybrid quantum classical systems. Software updates that could transform your research workflow. But wait, here's what most people miss. This collaboration quietly challenges the dominant, quantity over quality, approach in qubit development. Instead of just packing more qubits onto chips, they're fundamentally rethinking how we use the qubits we already have. Does this signal an industry-wide shift in priorities, or is it a niche strategy? We're asking readers, would you prioritize error correction improvements over raw qubit count increases? Share your take in the comments. Free registration unlocks. Asterisk the 2024 Lab Informatics Survival Guide. Asterisk expert panels on quantum AI convergence. Asterisk real-world success stories from engineering teams. Already registered? Jump straight to the member portal. Rest assured, your data stays protected under Europa Science's strict privacy standards. So, game-changing collaboration or interesting detour? The answer might determine whether practical quantum computing arrives in 5 years, or 15.